Sorry, the speaker will be shortly here. Okay, so let's welcome Markus again.
Yeah, hello, good morning. It is my great pleasure to be here and tell you a bit about our recent experimental results. I'm really honored to be invited here, and I really love the city. It's my first time here, and so it's really exciting to see that. Yeah, so I will be telling you about how we can use quantum gas microscopy to really go into new endeavors, and I will give you an update about all the work that is happening in our group on that topic. With quantum gas microscopy, we can do ultra-cold atom studies where we can really have full access to all the individual particles in the quantum gas, all the degrees of control, but at the same time we can have quite many particles, and so this is really a game changer in that sense. So the, here you can see a typical picture, for example, where you see all the individual atoms of the gas. We do that by high resolution microscopy. Each atom scatters a lot of photons that we detect. And then we can use quantum gas microscopy to analyze the system, but also prepare the system in intricate ways. Here, for example, we have just prepared a row of atoms here, and then we can just watch how the atoms move in the lattice, for example. In this case, they just coherently tunnel horizontally, and so they do a quantum walk. But let me show you something where we do a twist to it. If you tilt the potential, they do a quantum walk, but they actually do a Bloch oscillation. So the atomic wave function spreads out over many lattice sites, but then it should come back coherently. And if everything is coherent, it should come back to the exact same site. So let's try that. If the atom starts to tunnel, it spreads out here, and we see it in each realization at different location. But then, as you can see, it comes perfectly back to the original position. And that shows you this Bloch oscillation in real space. That shows you how coherent these ultra-cold atom systems can be. Okay. In my talk, I will be telling you about three things, about three new endeavors, essentially. In the first part, I will show you how we can use quantum gas microscopy to measure things that you didn't really, or that people didn't really think would be measurable, namely state purity and entanglement. In the second part, I will be showing you how we can apply these ideas and study and carry out experiments at the foundation of quantum statistical physics. And finally, I will be telling you about experiment with fermionic atoms, where we can really do quantum simulations of systems that you cannot calculate anymore. So, as I said, we have ultra-cold atoms in optical lattice. They tunnel through the lattice, they interact with one another. Then they can be bosons or fermions. Let's start with bosons here. For bosonic atoms, for weak interaction, atoms are delocalized over the whole lattice. They form a superfluid. Or if the interaction becomes strong, then they localize to a mod insulator state here, for example. We can take pictures of that and directly study that. The quantum gas microscopes looks like this. We typically work with two-dimensional quantum gases in the focus of a high-resolution imaging optics. And then we can use this optics to image individual atoms, but also to project arbitrary potential landscapes. In fact, all our lattices are actually imaged, an imaged mass that defines the lattice. And but we can also extend this to create arbitrary potential landscapes with a spatial light modulator. So essentially, we use the kind of chip that you have inside these video projectors that, as you can tell, has pretty good quality. And we can use it to project a picture, or in our case, we even use it as a hologram. And so then we can really define a microscopic wave function of the light with perfect resolution and extremely high precision in the plane of the atom. Okay. We can use that then to really engineer more fancy systems. For example, we start with a mod insulator where we have pretty much zero entropy, and then we can stamp out a little part by loading it into, by replacing this lattice with a double well or a quadruple well that we create with a spatial light modulator. And so that way we can prepare interesting systems. For example, 2 rows of atoms, but only 4 atoms long, box potentials. Like pretty much we can do whatever you want there. So these are the techniques. This is our workhorse. And let me show you how we can use this now to measure entanglement. Okay. Why would we want to measure entanglement? Well, I mean, one reason is if you think about exciting states of matters, like spin liquids, for example, topological states of matter, those states of matter, they cannot be described with a simple broken symmetry. It turns out that they all have genuine multiparticle entanglement. And so that would be really great to measure that, to characterize those states. In theoretical physics, that's being done a lot. But unfortunately, in experimental condensed matter physics, for example, that is not at all possible. I'm sorry, I'll go to the... Right. Actually, let me mention the people on the experiment first. So the experiments on measuring the entanglement entropy were led by Rajibul Islam, and this is the team here, and Eric and Matthew are here in the audience also. Okay. So these exotic states of matter, they have all non-trivial entanglement, but how could you measure that? In traditional condensed matter experiments, you cannot measure that, or at least there's no known way so far to access that. But let me go back a step. What do I mean by entanglement? Normally, we think about entanglement in a spin system, for example. And there things are a bit easier, but here we have a many-body system of itinerant particles, so we really have to think a little bit what we mean by entanglement. I define entanglement, or I think about entanglement as the rejection of a local reality. What do I mean by that? This means that, for example, if we share a bell pair, then, as you know, whatever measurement we do, we will always find the 2 spins looking into the opposite direction. But that means that if I just look at my spin by itself, I cannot describe quantum mechanically. It would just be a totally mixed state. It's totally random what it will do. You have to consider this non-local object of those 2 delocalized spins if there is entanglement between the systems, so there's no local reality, essentially. These could be spins, but they can also be, more generally, you get the same effect if you have a particle delocalized. Like, if I have a particle delocalized between you and me, then the state looks the same, essentially. There are some subtleties to it, but at the end of the day, this is really pretty much the same thing. And if you have questions for that, you can ask me after the talk. Okay, so it was hard enough to quantify entanglement for like 2 particles in quantum information, for example. How can we quantify entanglement here? Let's go back to the definition of rejection of local reality and say, whenever I cannot write my quantum state locally, then it has to be entangled. And what that means is, like, imagine you have a pure quantum state here. If it can, if I split my system into 2 parts, A and B, if it can be written as a product state of A and B, then I can write it locally and there's no entanglement. Okay? So the clicker has problems today. So if I then trace over one part of the system, because the state is separable, this state will remain a pure state. But if there is entanglement in the system, here, for example, if I have particles delocalized, if I have exactly 4 particles delocalized in the system, then the state cannot be written as a product state between A and B. And if I trace over B, then this state in part A will turn into a mixed state. And the amount of entanglement between A and B is quantified by how mixed the state will get. The more entanglement there is, the more this state will be mixed. If there's no entanglement, it will remain a pure state. So in this bipartite entanglement, the mixedness tells me about the amount of entanglement. How do I quantify mixedness? Well, you all know the state purity, right? So let's go with that. Let's use state purity. And if I take minus logarithm of the purity, that's the so-called second order Reiner entropy. So it's just the mixedness expressed as an entropy. Okay. There are other ways to do it. It turns out the nicest way is the von Neumann entropy. This is going totally berserk here. The nicest one is the von Neumann entropy that you see here, which is trace of rho log rho. But of course, that's a bit more complicated experimentally. But you can think of this being the leading order approximation of the von Neumann entropy. Okay. So if I could measure this purity here, then I could tell entanglement. I could show that the whole state is pure. But then I could see that if I only measure part of the system, I will find a mixed state. And proportional to that mixedness, I know I'll have to have entanglement. But the problem is, can I measure purity of a state? Well, normally you cannot. Purity is not an observable, right? Trace of rho square. An observable is always trace of rho times the operator. So purity is not an observable. So a lot of people would have actually argued you cannot measure that in principle. Okay. Well, it turns out we can. We can do this by things that we know from quantum optics and atomic physics, namely by using multiparticle interference. And in order to illustrate that, let me go through the famous good old Hongu-Mandel experiment, because what we are going to be doing is a generalization of that. If you have a beam splitter and 2 photons hit the beam splitter, if and only if those 2 photons are indistinguishable, they will always end up on the same side after the beam splitter. That's the famous Hongu-Mandel experiment, 2 left or 2 right, but never 1 left, 1 right for symmetry reasons. Okay, but this only happens if the 2 are indistinguishable, and indistinguishable means they are identical pure state. So in a way, this is already measuring the purity or the like how identical the photons are. Okay. The trick is now to extend this to, well, first of all, we can extend it to other particles, like 2 atoms in a double well or so, and Adam Kaufman, Cindy Riegel, or also in France, there were exciting experiments on that. But then we can also extend it, how about not just putting in 1 particle, but actually a many-body state. And surprisingly, that works beautifully. If you put 2 many-body states onto a beam splitter, and you'll see what I mean by that, then if the 2 many-body states are indistinguishable, you will get even particle numbers out on both sides of the beam splitter. That's the generalization of Hongu-Mandel interference. Okay. And all these odd parts, they cancel. Well, this is amazing. If you think about it, we can now actually measure how identical the 2 many-body states are. Normally, that would be very hard. You would have to try to do some state tomography. If I give you a many-body state and I have one, how can we tell if they're the same? Normally, we can't, right? You can only measure certain things. But now we take the 2, put them on a beam splitter, and if they are identical, we will always get even particle numbers out. So that's a pretty strong statement. And it's actually really simple at the end of the day. Because if you do that, then the parity is equal to the quantum state overlap of the 2, trace of rho 1, rho 2. Like, I was really surprised when I found this out. And if the two are the same, then this is the purity. So by quantum comparing two many-body systems, interfering them and looking at the parity, we can measure the quantum state overlap, or we can measure the purity. Okay. Two systems to compare, quantum compare, essentially. That's the new thing here. I think this is going to be useful for a lot of different things, because just measuring quantum state overlap of a many-body state in general, we're already doing this on systems with a Hilbert space size of about 1,000, and I think this could be scaled up quite a bit. This could allow you to do a lot of interesting things. I will focus on just measuring the purity now in the rest of this talk. Okay, let's try that experimentally. So if we have, we prepare two identical systems. We started pretty small, like 4 atoms on 4 lattice sites, for example, in the Bose-Hubbard system. Okay, and now we need a beam splitter, and the beam splitter, you can do with evanescent coupling, like a fiber beam splitter where you bring 2 fibers close, right? And you also know a beam splitter can have multiple modes. So this we can tunnel couple. If you turn off the dynamics and the interaction, then we can tunnel couple neighboring lattice sites here to create a multi-mode coherent beam splitter between the two systems. Okay. Each lattice site, each row is one mode here. Okay. Let's look at one of those modes. If I just prepare it with 1 particle, then I have the original Hongu-Mandel experiment. Okay. And if you do this 1-1, then we see that we get these totally coherent oscillations, 1-1, 0-2 plus 2-0, 1-1, 0-2 plus 2-0. This is the classical Hongu-Mandel kind of signature. And at this time here, this is when I have a beam splitter in Hongu-Mandel. So I turn 1-1 into 0-2 plus 2-0. Okay. But the beautiful thing is that I can now say this is a multimode beam splitter, and I can actually do this with many-body physics. And in the simple case of 2 mod insulators, I can now interpret this as a many-body Hongu-Mandel by just saying, okay, let's have a look. Let me just add up the parities of the different modes of the beam splitter. And the fact that in each realization, globally, I always have even particle numbers here, means that globally, these two states are pure. And I can also add up just a subsystem. Here, in this case, they would be locally also pure because I'm starting with a mod insulator here where there's no entanglement. So the whole state is pure, the mod insulator, but if I cut it into 2 parts, it's a product state, and it will still be pure. Let's look what happens if I let the atoms tunnel, if I delocalize them. 4 particles delocalized here, like a superfluid with fixed particle number. Now they will, things will look very different. On a single site, I will not get this, clear signature of always even particle numbers. It could be odd or even, totally random. Okay? And in fact, if I look at a local system here, it can be odd or even, but odd or even means it's a mixed state, so it's quite mixed. But amazingly, if I add them all up, like on the right side here, they will add up to even if and only if these 2 many-body states are identical. That's a really strong statement. I can predict the outcome of the last beam splitter pair here. Okay? If these have all been even, then I know this has to be also even, the last. If they have been odd, I know this is odd. But if I change any many-body phases here, then this would not be the case anymore. Okay, so I can really, by looking at the parity, I can quantum compare 2 many-body states. This Hilbert space size is already a few hundred, and later I show you data on bigger systems. So, even if you didn't, even if you couldn't follow the details here, let's look at this. So here we have measured from a mod insulator to a superfluid. We can measure entanglement entropy directly now. Here I vary the tuning parameter like the interaction, and now I'm looking at the purity of the whole system. And if it's if the parity of the measurement is always even, it's very pure. And across this transition, the system stays pure. But if I look at the subsystem 1 or 2 sites, for the mod insulator, a subsystem is even more pure, and that means there's no entanglement. But on the superfluid side, with fixed particle number, the local part of the system is less pure, or here I have a state that's more pure globally than locally, and that's a direct evidence for entanglement. That can only be if there is entanglement that I have a higher purity globally than locally. And so I can measure this directly, and this is a measurement of entanglement entropy. We have done all kind of different things with that I don't have time to talk about, but I can refer you to this paper if you're interested. Let me now show you how we can use these ideas to study quantum statistical mechanics. Okay? These experiments have been led by Adam Kaufman and pretty much the same team with some new members here. Right, so what do I mean with quantum statistical mechanics? What I'm interested in is the question, what happens if I have a closed quantum system? Normally in statistical mechanics you always consider having a bath or so, but let's not do that. What if I have a closed quantum system and I quench that quantum system? I perturb it somehow, and then I look how it thermalizes, or if it thermalizes. Okay. Well, let's have a look. So this is my quantum system, and locally it's so it's a pure state, and locally it's at 0 temperature essentially. But now I hit it with a hammer, so I do a quench. For example, I change the ratio of tunneling and interaction quickly. Well, but this is like after I do that, it will actually undergo unitary dynamics. The many-body state was in a pure state, and after I change my parameters, it will still undergo unitary dynamics, so this will remain a pure state. But what's amazing is that you can find that locally, you still get that local observables tend to very quickly look thermal. How can that be? How can a state that is globally in a pure state, like no entropy, locally look like a thermal state, which you would associate with maximization of entropy? So let's look into that problem experimentally. My system is now 6 atoms on 6 lattice sites. I can do a quick quench, and after that, all the atoms tunnel like crazy. It's a very complicated state. The Hilbert space size is nearly 1,000. Okay. Well, I expect this to remain in a pure state afterwards. The nice thing is I can show this directly now by using 2 copies and doing Hongo-Mandel interference. Here you can see it remains in a pure state. So this is the time after the quench. This is the purity that I just measure again as the parity of the beam splitter. Or I can express it as an entropy here, which is minus log the trace of the purity. And I see the purity is very close to 1, and it remains there. Okay? It remains a pure state. At the same time, I can also look at local observables. For example, on a single side, let's just count the particle numbers, for example. That's a nice observable. And amazingly, I will find that very quickly after this quench, they look completely thermal. This is my measured number distribution, looks completely thermal. Looks exactly like what you would expect from your favorite thermodynamic ensemble. Okay, so how can that be? Here, I see clearly there is no entropy in the system. It's a pure state. It remains a pure state. But here I see, well, but locally it looks thermal. But thermal means maximized entropy. So how does that go together? The beautiful thing is, let's actually have one closer look here at this. We can actually measure the overlap of the local density matrix with the thermal density matrix. Like here we measure, initially the local density matrix is quite distinct from a thermal state, but then very quickly the trace distance here becomes 0. So here we measure the trace distance of the state over time, and very quickly it becomes very thermal, or the fidelity, very quickly it's like 98% or 99% a thermal state. Okay. Okay, so how can that be? Key of understanding this is the entanglement entropy I was just telling you about. Let's measure the entanglement entropy after the quench and how it changes in time. Here is the entanglement entropy of one side, right? Very quickly after the quench, it will rise, but then it will plateau the entanglement entropy. How about 2 sides? for two sides, I see that it goes up to about twice the value, and then it plateaus. For three sides, it goes up to nearly 3 times the value, and then it plateaus. Well, what if I keep going? For all sides, of course, it remains pure. So there's no entropy arising at all, as I was showing before. Okay, let's plot this versus the system size. So here I vary the system size from small to large, and I see that the entanglement entropy goes up and then goes down, just completely symmetrically. The total state is still pure, but initially here, if I look at a subsystem, it appears as a mixed state. The key to understanding is to identify this entanglement entropy with the thermodynamic entropy. Because let's look, if I just measure the temperature from the number distribution, and I plot what would I expect in terms of thermodynamic entropy, classical entropy, then there would be this line here, okay? So the entanglement entropy is just playing the role, like for small subsystem here, for small subsystems of 1 and 2, and well, 3 still kind of, my entanglement entropy looks just like the thermodynamic entropy. It's volume law entropy, which increases linearly with system size, okay? But if I go to a bigger system, then this entropy will disappear again, and at the end, I have a totally pure state again, okay? So entanglement entropy has a lot to do with this thermodynamic entropy here right. In fact, I can think about this. So the beautiful thing is now, if I do such a quench, even though the total state is in a pure state, a small sub-area is indistinguishable from a thermal state, right? If you have this kind of volume law and entanglement scaling, which is pretty remarkable. At the end of the day, you could even say this, you could consider this a mini version of the universe, essentially. Well, first of all, you notice that you don't really need an external reservoir. The reservoir can be, this part of the system essentially acts as part of the reservoir. And if you want, you can push it all the way to the limit and say, let's just assume for a moment the universe was in a pure state. I think even the question if it is or not may not make sense, because as you know, we cannot measure the purity unless we have two and interfere them, and I don't think that could be done. So, but let's just assume that for a moment, that the universe is in a pure state. The amazing thing is then, this would show you that any system smaller than half, or any observable that depends on less than half of the degrees of freedom of the universe would appear thermal, or could appear thermal if you have this kind of volume law behavior. Okay, but how can it be if there's so much entanglement? How can it be that there is no weird effects from that, right? Like, is there any, if there's entanglement everywhere, is there any kind of weird spooky action in a distance or so left, what we normally associate with entanglement? No, there's not at all. Because volume law entanglement, where the entanglement grows proportional to the volume, is just has the amazing property that it doesn't create any correlations. You can define the mutual information SA plus SB minus SAB, which quantifies the sum of all correlations, classical or quantum. And you see, if the entropy is linear to the volume, then SA plus SB minus SAB is 0. So that means as long as this grows linearly here, or as a volume, there is no correlation between two parts. Like A and B will be completely uncorrelated. So everything's fine again, right? Even if the universe was in a pure state, any two subsystems that have less than half of the degrees of freedom will behave completely uncorrelated, classical, or whatever, if things were in thermal equilibrium. And only if you go past that 50%, then this mutual information will get large again, and I will get a lot of correlation. And at the very end, I even get correlations that you cannot explain classically, quantum correlation. So volume law entanglement means no correlation whatsoever. If you want entanglement that you want to use for quantum computation or so, you need area law entanglement. You need entanglement that goes up quickly and then remains flat. And we have also done some experiments on some examples of that. Okay, I don't really have time to tell you about the physics behind it, but essentially, let me just mention, let me just skip this and mention that let me just mention that this can be explained by eigenstate thermalization hypothesis, what I was just telling you about. The idea is that you get that this scaling of the entanglement entropy you get already if you just consider one randomly picked eigenstate of the Hamiltonian. The green line here, which is pretty much identical, right, is just take one random eigenstate that has about the right energy corresponding to how much energy you put in. It doesn't matter which one, right? And that alone will already look thermal. That alone will already have this behavior. And so this quantum statistical mechanics, which is behind this, ETH, is essentially telling you you can use chaos, kind of the chaos of the eigenstates. That's where kind of chaos comes in. And the remarkable thing is that even a random eigenstate already looks like that. And there's a lot of active research on understanding this much better. When is that the case? Is it always the case? It seems to be pretty much always the case. The only known counterexamples are an integrable system or many-body localization, which is more or less also a special case of integrability. Okay, so I was really very intrigued learning about these things in this context of these experiments. I think these are really interesting ideas, and I have a feeling that statistical mechanics can actually be much better understood with these kind of entanglement concepts. And because in classical statistical mechanics, there are lots of problems that you do assumptions in the beginning that you can't really justify, like ergodicity. Here, this seems to become a microscopic theory that can explain quantum statistical mechanics. Okay, so let's totally switch gear now. And so I showed you how we can study this entanglement and so on. But let's look at a different system. I was always talking about bosonic systems. Let's look at fermions. The team of the experiment is shown here. Daniel Greif is the current postdoc, and the people who really built the experiment over the last 8 years also include Sebastian Blatt and Florian Huber. And Maxwell Parsons, recently graduated. Christy and Anton are here in the audience also. And Jeffrey started last year. Let's study fermionic atoms in an optical lattice. What you get then is this famous Fermi Hubbard model. So we have fermions in two spin states. They tunnel in the lattice, much like the bosons, but they also interact with one another. This gives rise to a very interesting phase diagram. There are actually many open questions, but what is certainly known is that there's an antiferromagnetic state. What is strongly believed is that there is a superfluid phase, but it's incredibly hard to calculate these things microscopically. There are also many papers that suggest all kind of other phases here. One interesting aspect of this model is that it's closely related, as you heard in the talk of Randy Hewlett already, to Q-bridge physics, because, I mean, just the phase diagram looks so similar, essentially. You have D-wave superfluidity in the vicinity of antiferromagnetism, and then, right. So this would be a great opportunity to study this better. This is an experimentally determined phase diagram, but people don't really understand what this actually means. You can tell by the names, with strange and pseudo, but the idea is, can we understand this microscopically here, and how much of this is already contained in the Hubbard model? So this is a great experimental opportunity because it's really hard to calculate these kind of things. It was proposed in 2002 that this model could be pretty much perfectly realized with ultra-cold atoms in optical lattices by these colleagues you all know well. And a lot of exciting experimental work has been going on. I will mention some of that in a minute. Our experiment, our goal was to combine these optical lattice experiments with fermions with a microscope. So here's our quantum gas microscope that we built over the last 8 years. Here, this is a view. This is a vacuum chamber and a view inside that high-resolution objective with a very large NA. And the trick is then, with lithium, it's harder. They're so light and fluffy. We need extremely strong lasers with hundreds of watts of laser power. And then we do Raman sideband cooling to scatter photons as we hold on to the atoms on the lattice sides. So in the next talks, you will actually hear much more about that and also how difficult that is to do. In 2014, we had the first promising pictures. You can kind of start to see individual atoms. Then a year later, we got it to work. And you can now see each of the dots is exactly one atom. And in fact, the year 2015 was really the year of fermionic quantum gas microscopes. There were 6 different microscopes all over the world that started to operate last year. And so this is a really exciting time for this topic. Of course, here these pictures are still hot atoms, so the next step then was to get cold. And here we see a fermionic mod insulator that pretty much has 0 entropy. There's exactly 1 atom per lattice side. We first looked at this charge physics here. So you can see you get different phases. For example, a metallic phase if the fermions are delocalized in the lattice. But then also if you have 2 atoms, if you fill the band more, at some point there can be at most 2 in the lowest band, right? 1 spin up, 1 spin down. That's a band insulator. This shows up here in the center with 2 atoms per side, which appears bright here in the parity imaging. Or if the atoms repel, you get a mod insulator, which you can see here. It's actually perfect mod insulator because all the entropy went into the spin degree of freedom here. Right. Okay, but how about magnetic correlation? The exciting thing about the Fermi Hubbard model is that you have this intricate interplay of magnetism and motion of particles. Particles want to anti-align, or like to magnetically anti-align to form singlet kind of states that locally look like singlets. And there has been great experiments, for example, by Tillmann Esslinger, who was able to observe this as local singlets, or Randy Hewlett, as you heard in the night's talk, who's using Bragg scattering to look for antiferromagnetic ordering. These experiments have gotten pretty close to the 3D transition temperature, T-nail here. They're still a bit above, but nevertheless, you can actually see already pretty strong local antiferromagnetic correlation, like next nearest neighbor correlation. Okay. Well, how about in the microscope? Can we see this in the microscope? Normally, well, the first thing to keep in mind is that we are actually not, so the state is called antiferromagnetic. It's an antiferromagnet, but it's more like a Heisenberg magnet. It's not just your perfect checkerboard, because there's no defined quantization axis, kind of. Right? And that actually means that at most you expect 36% nearest neighbor correlation of like opposite correlation. So it will never look like a perfect checkerboard unless you break the symmetry somehow. Okay. Okay, but what can we see? This is a picture with where we look at all the atoms, but we can do a trick. We can blow out one species of atoms and then just look at one spin state. And if you do this, voila, we get pictures like this. And you can see already that it already looks a lot. You can already see by eye a lot of antiferromagnetic correlations here. So we were really excited to see that. You don't see it as strongly in every single shot because it's kind of like each shot picks its random quantization axis, and sometimes you're just right locally, and sometimes you're not. It's interesting, actually, to even understand, to try to understand what would you expect to see. But we can measure the antiferromagnetic correlation, and we see that we get correlation over 2-3 sides, kind of. Okay. We can measure two-dimensional maps of that. Let me not get into detail. Let me just point out we can do very precise. We get extremely good agreement with theory. Well, but theory only exists for half filling at those cold temperatures because of the sign problem. this can hardly at all be calculated, or it's extremely difficult to calculate anything away from half filling. But here, of course, we have all fillings, and so we can really start to study things that cannot be calculated. We see a great agreement, but this is really a new door. There is a lot of exciting experiments now. So this experiment I'm talking about, there's also, briefly after we put this onto archive, the experiment in Munich also got one-dimensional antiferromagnetic short-range correlation, and the same in Martin Zwirlein's group, and I'm sure you will hear more about that. Oh, right. Okay, well, is that it, or can we get colder? As Randy Hewlett already told us in his talk, the idea is you could engineer the entropy. And so what we tried here is very similar to what he's also working on, that we create a more fancy potential here using a spatial light modulator, where we have metallic wings that can suck up a lot of entropy, and the core should then get colder. So let's see what happens if you try that. Here's a picture. We have a dense core and a thin metal with like 20-30% filling that can take a lot of entropy. And let's look at the antiferromagnetic correlations now, and we actually found it looks pretty perfect. So here you see very nice long-range antiferromagnetic, like pretty long-range antiferromagnetic correlation. You can see that by overlaying this checkerboard here. Most of the atoms fall within this checkerboard, even many lattice away, and we can quantify this and measure the correlation length. And you now see antiferromagnetic correlation on a much longer scale here. We can also extract the temperature, which is now, we have a 2D system where there's no sharp transition, but these temperatures are below the 3D transition temperature, right? We also started to study dynamics, like quantum walk, which gets really interesting because those holes behave in really interesting ways. Okay, so this is a new kind of it's a really exciting time because now we can really start to study things that cannot be calculated. The lifetimes are fantastic. The spin correlations live for 1.5 seconds, but the tunneling rate is a kilohertz. So the atoms tunnel 20,000 lattice before the spin correlations disappear. So there's a lot of, I'm very optimistic there will be a lot of exciting physics to study. Let me just advertise a poster. This is on topological states in a ladder where we can now also enter strongly interacting physics. And yeah, so I showed you these 3 topics: entanglement, quantum thermalization, and totally new possibilities with fermions. And I would like to thank all the students and postdocs involved in the work, and the collaborators, and the funding agencies. And I would like to thank you very much for your attention.
Thank you for this very nice talk. Are there any questions?
There's one here.
This is a very, really wonderful talk. So may I ask you for the definition for the pure state? You at the beginning you introduced the pure state. But for pure state, for density matrix, there is a definition. That means trace of rho square equals rho. So the rho is the density matrix. So I think in the experiment, is it possible to measure trace rho square equals rho? So this is a very strictly definition for pure state.
Rho square equals rho, yes.
Yeah,
exactly.
yeah, the trace. This is the pure state. Yeah.
Right.
Mm-hmm. Yeah.
Right. I mean, that's essentially what we're using. I mean, what we are really testing is whether the 2 states are indistinguishable. Like we measured the quantum state overlap between the 2. Right. We do this by with the interference. We can do that. Right. But if the state overlap is large, then this gives us a lower bound for the purity, essentially.
Okay.
Okay, maybe one last quick question.
Just to follow up on that, I guess it's the statement that the purity of a state is not measurable. Is that really true? If you can measure the elements in the density matrix, then if rho squared is less than 1, it's not a pure state. Is that not a measure of the purity?
Okay, right, so one has to be, right. Well, I guess you're referring to state tomography, or so yeah. If I have many copies of state, of course, right, then I can extract things. And in a way, I'm also doing this here because I have 2 copies that I interfere, right? What you normally do in state tomography, instead of interfering 2 copies, you take a lot of copies and all interfere them with a coherent state, or they're not necessarily coherent state, but with all kind of different states. So you can view that as that kind of same interference, but instead of interfering 2, you're interfering with a lot of different known states, and that way you can do state tomography and figure out the density matrix. Here, the nice thing is we can measure the purity without having to do that, because for itinerant system, there's not even a known way to do that. I wouldn't be surprised if we could construct something like that, okay? But the beauty is we can directly see if 2 states are identical or not without having to do this painful tomography, essentially. Yeah, right. I mean, right. In both cases, to say anything about the purity of a state, you need many copies of it.
Okay, so let's thank Markus again and welcome the next speaker. So the next speaker is Stefan Kur from Strathclyde University.